So we've talked about acids and bases in the past, and in the past we talked about Arrhenius acids and Arrhenius bases. We said that Arrhenius acid was anything that had an H plus ion, and we said an Arrhenius base had an OH ion. Now it turns out these definitions don't work for all acids and bases. So Bronsted-Lowry came along and he modified those descriptions. He said that what we can have is a Bronsted-Lowry acid, and he said in this case it's going to be a proton donor. Now remember, we said that an H plus ion was also called a proton because a hydrogen atom has one proton, one electron, no neutrons. Once it gets rid of its one electron, it's just a proton. Now, Bronsted-Lowry acid is pretty much the exact same thing as an Arrhenius acid. It's something that's giving up an H plus ion. Where his definition differs is the base. He says that a base is a proton acceptor. And the big base that came about with this definition was ammonia. Ammonia is NH3. Doesn't look like it should be basic, but it is. If you put in a pH meter, it's going to read higher than 7. The reason is this can accept an H plus ion and form ammonium like this. So while it is not an Arrhenius base, it doesn't have an OH, it is a Bronsted-Lowry because it can accept a proton or an H plus. Okay? Now, we can perform acid-base stoichiometry calculations pretty much just like we did with precipitation reactions. Okay? We're still going to need to do similar things. We're going to have a balanced reaction. This says net ionic. I usually write them complete. Either way works. Again, I am going to change liters to moles. If I have more than one reactant that I have information about, I need to determine the limiting reactant. I'm going to change moles to moles using my balanced chemical reaction. And then I'm going to change moles to grams or moles to liters, depending on what the question asks about. Okay? Now, sometimes you'll see this written as an acid-base reaction. Sometimes they'll use the word neutralization reaction because in a neutralization reaction, I'm taking my acid, I'm taking my base, they're neutralizing each other to form water and some salt. Okay? So here I've got my acid-base reaction. What volume of a 0.100 molar HCl, hydrochloric acid is my acid, is needed to neutralize 25.0 milliliters of 0.350 molar NaOH. So I've got NaOH. Now, in an acid-base reaction, the H from my acid is always reacting with the OH from my base. These are Arrhenius acids and bases to form water. It's pretty easy to balance. 1 H plus 1 OH forms 1 water. Na is a +1, Cl is a -1, so I'm making NaCl. I'm told that I have a 0.100 molar HCl solution. I'm told that I have 25.0 milliliters of NaOH, and it's 0.350 molar. Okay? Now, whenever I'm working with a problem, whichever one I have more information about, that's the one I'm starting with. Okay? So they tell me a lot more information. I know how much and the concentration. Here, I just know the concentration. Okay? I'm trying to find the volume of this one. I'm probably going to solve for it in liters, but we'll see what happens. Okay? So, I've got my volume and I've got my molarity. Well, because my molarity is moles per liter, step 1, change milliliters to liters. So 25.0 milliliters. I know that there's 1,000 milliliters for every 1 liter. Always change milliliters to liters first. The reason I have to do that is I know that I've got 0.350 moles of NaOH for every 1 liter of NaOH. Okay? Well, I don't want to know about NaOH. I want to find out about HCl. Now, I know that I've got moles of NaOH, and I've got one of them according to the reaction, reacting with 1 mole of HCl. Remember, I'm always looking at my balanced chemical equation to change moles of one element or compound into moles of another element or compound. Now the final step, I'm finding volume. So I need to make moles of HCl go away. I want liters of HCl. Now in the problem, here's my molarity. Moles of HCl per liter of HCl. So I know that I have 0.100 moles of HCl for every 1 liter. If I plug this into my calculator, 25 divided by 1,000 times 0.350 times 1 divided by 1 divided by 0.1, what I should get, oops, I forgot to plug this into a calculator. What I should get is, 25 divided by 1,000 times 0.350 divided by 0.1. I get 0.0875 liters. Now I can leave it like this, or because originally I was in milliliters, I can go back to milliliters, make my answer make a little more sense. 1, 2, 3. 87.5 milliliters of 0.1 molar HCl. Okay? So it looks pretty much the same as we did with precipitation reactions, only now I'm using molarity more than once. Okay? So let's look at example 2. I've got 28 milliliters of 0.250 HNO3. I've got 53 milliliters of 0.320 molar KOH. I want to calculate the amounts of water formed in the resulting reaction. Okay? So, this time I have information about 2 different reactants, so I need to do 2 different calculations. First, I need my balanced chemical reaction though. HNO3 is reacting with KOH. Again, the H from my acid reacts with the OH from my base to make water. K plus NO3 plus 1 minus 1, that balances nicely. I'm going to do 2 calculations. In both calculations, I'm going to change to water that's forming. Okay? Now, it doesn't give me a concentration for water because water doesn't have a concentration. So the amount, I'm going to change this to grams. Maybe not. Maybe moles. Let's see. So what I'm going to do is I've got HNO3, I've got 28 milliliters. Again, step 1, I want to change milliliters to liters. So I know that I've got 1,000 milliliters for every 1 liter. Okay. Once I make my volume turn into liters, I know that I've got moles. I've got 0.250 moles of HNO3 for every 1 liter of HNO3. Okay. Well, now the problem doesn't ask about HNO3, it asks about H2O. Okay, so I know for every 1 mole of H2O, I'm making 1 mole of HNO3. And I said that backwards. It's actually 1 mole of HNO3 makes 1 mole of H2O. Same difference. Okay, let's go ahead and stop at moles, and I'll tell you why once we get to the excess ions. So, 28 divided by 1,000 times 0.250, 1 over 1. I plug this in, and I get 0.007 moles of H2O. Okay, so let's take a second and do the same thing for KOH. Solve for moles of H2O formed from moles of KOH. So I should have had 53.0 milliliters KOH. Again, step 1, I'm changing it to liters. I know that it's 0.320 molar, so moles of KOH for every 1 liter of KOH. I know that I've got 1 mole of H2O for every 1 mole of KOH. When I plug this into my calculator, I should get 0.01696, which I'm going to round to 0.0170. I need to keep 3 sig figs, moles of H2O. Okay, so if I look, I've got 0.007 and 0.017. This is smaller than this, so this is the maximum amount of water I can form. I could change it to grams. They don't ask for grams, they just say amount, so I'm going to go ahead and leave it in moles. HNO3 is my limiting reactant. Now it does ask me a second question. It says, what is the concentration of H plus or OH ions in excess after the reaction goes to completion? Well, HNO3 is my limiting, so all of my H plus got used up. My OH is the excess. So let's figure out how much excess. I could have used it to make 0.017 moles of H2O, but I can only make 0.007 moles of H2O. So if I subtract those two numbers, I find out that I've got 0.01 moles extra that did not form. That's H2O. But I can work backwards. I know that for every 1 mole of H2O, there's 1 mole of KOH, 1-to-1 ratio. I know for every 1 mole of KOH, there's 1 mole of OH. So if I had 0.01 moles of H2O extra, I've got 0.01 moles of OH in excess. Okay? So remember, it looks basically exactly the same as our precipitation reaction. The only difference is if I'm given milliliters, I need to change it to liters.